In this video, I'll show you how to solve the ALEKS problem called Understanding the Meaning of a de Broglie wavelength. So this problem is going to give us 4 different objects, and it's asking us to determine if we can describe those objects using classical mechanics or if we need to use quantum mechanics to describe the motion of the object. The problem is going to give us an alternate value for Planck's constant. Mine here is pretty close to the true value, but I have noticed when I look through these problems that this number does fluctuate. It's different for every problem. So make sure that not only are you not using the actual value of Planck's constant, don't necessarily use this value either. Make sure you're using the value given to you in the problem. So how are we going to use this information to determine if the object can be described with classical mechanics or if it needs quantum? To do that, we're going to be comparing the value of the de Broglie wavelength. That's abbreviated with the symbol lambda. We're going to compare the value of the de Broglie wavelength to the object's size, either the object's length or the object's width. ALEKS sometimes describes it as a length, sometimes it describes it as a width. If the de Broglie wavelength is greater than or equal to the object's size, then in that situation we need quantum mechanics to help us describe the motion of that object. So what we're going to do for each of these objects is calculate the value of the de Broglie wavelength, compare it to the object's size, and then we'll know if it's classical versus quantum. So the de Broglie wavelength is calculated by taking the value of the Planck's constant, and remember we're using an alternate value of Planck's constant, dividing it by the mass of the object times its velocity. The mass of the object needs to be in units of kilograms, and so most of these problems are going to require you to do a unit conversion into kilograms. The velocity or the speed of the object needs to be in units of meters per second, and you're going to need to do some unit conversions there as well. Let's go ahead and do this calculation for my first one, which is the mosquito. So this tells me that I have a mass of 2.4 milligrams. Right off the bat, I need to do a unit conversion because that is not the correct unit for plugging it into this equation. I need my mass to be in units of kilograms. So I'm going to actually just do this conversion by hand, although if you want to save time, you can just type it into Google. You can have the internet do this conversion for you. Let's see, I don't really have room there to do it. 2.4 milligrams, I'm going to multiply by a conversion factor that lets me cancel out the milligram and convert into gram. Milli is the prefix for 10 to the minus 3, which means 1 milli is 10 to the minus 3 of anything. And then I need to do a 1 more conversion, converting out of grams into kilograms. Kilo is the prefix for 10 to the 3. And so plugging this into my calculator, I'm going to get 2.4 times 10 to the minus 6, but I'll show you how I put this in the calculator. 2.4 times 10 to the minus 3 divided by 10 to the 3, and that gives me, as I said, 2.4 times 10 to the 6, negative 6, and that is kilograms. So I'm going to go ahead and start filling this in for my mosquito. My Planck's constant value up here, 6.62607 times 10 to the negative 36 joules times seconds. Those are the units for Planck's constant. My mass, 2.4 times 10 to the negative 6 kilograms. Now let's see what I have for my velocity for this mosquito. This mosquito velocity is 2.4 meters per second, so that I don't have to change into different units. 2.4 meters per second. And now we're ready to do the math on this de Broglie wavelength calculation. 6.62607 times 10 to the negative 36 divided by 2.4 times 10 to the negative 6 times 2.4. I feel like I need to double check and make sure that I got that number correct. Okay, and that's going to give me a wavelength of 1.15 times 10 to the negative 30, the units are going to be meters. Now that can be a little bit difficult to determine, like where the units come from. A joule is a unit of units, so the unit of a joule is a kilogram meters squared over second squared, and you can plug those units in place of the joule, and then you will see that everything is going to cancel out except for one of those meter units, and that's where we get this from. All right, so now that we've got this calculated, our next thing is to compare the de Broglie wavelength to the actual length or width of the object my object has. I'm going to move my unit conversion out of the way here. So my object has a length of 11.8 millimeters. I really don't need to do a comparison. This is definitely smaller than 11.8 millimeters, but I'll just do it anyways. 11.8 millimeters. So in order for me to actually compare these two lengths, or these two widths, whatever you want to call it, they should be in the same unit. Now, because this is such a tiny, tiny number, I know that this 11.8 millimeters is going to be larger, but sometimes the numbers might be a little bit closer together, in which case it's just a good idea to convert so that they are in the same unit. You can either convert the length into the same unit as the de Broglie wavelength, or you could go the other way. You could convert the de Broglie wavelength into the same unit as the length. Milli is the prefix for 10 to the minus 3, so 1 milli is 10 to the minus 3 meters. So this is going to be 11.8 times 10 to the minus 3 meters, or 1.18 times 10 to the minus 2. And we can see that our wavelength for this problem is much smaller than our length. And then let's go back and take a look at how we're going to use that information. So if the wavelength is greater than the length, we use quantum to describe it. And that means that this object can be described using classical mechanics. So I'll add that on here. If the wavelength is less than the object's length or width, then you can use classical mechanics to describe it. Now, this is just a really tedious problem. There's just a lot of unit conversions involved as you're working on this problem, and then you get to the end and you still have to do some comparison. So give yourself lots of time. I know you can do it.